Hi, good morning all. So my name is Hessa. I'm gonna present our research work on the program abstraction and re-engineering using Agile model-driven engineering approach. So in this presentation, we are gonna define the Agile model-driven engineering approach, AMDRE, to re-engineer legacy systems, which has been used since 1990s. There is an automated abstraction of system to UML specifications, interactive refactoring and re-architecting to improve system quality, and have applied to a Visual Basic and COBOL legacy code. So the outlines, quickly, motivations for re-engineering, the obstacles, our AMDR process steps. We're going to go through the research questions and the challenge of legacy code abstraction. And also we are gonna demonstrate the case studies, the abstraction from VP and COBOL to UML and object constraint language. Also we'll see how we have maintained the quality analysis and restructuring, re-architecting, and then the evaluation of our case studies. And finally, we are gonna present the related work and how our work is distinguished. So the motivation for re-engineering, first, we know that legacy code systems mainly used for financial applications, which is our core case studies, but it requires significant resource to maintain. And also there is the requirements of necessary human expertise and supporting software may become unavailable. Those effective re-engineering tools is required, okay? So the main obstacles, as we said, high manual effort required for the engineering process, and also there is a need to assure semantic preservations of original code, and also there are wide range of re-engineering tasks that we have to follow due to large programming languages environments. So to address all these challenges, we tried to provide in our approach, we try to increase the automation via model-driven engineering to overcome the high manual efforts. And also we try to verify re-engineering steps. And finally, we try to reduce the complexity of the approach by providing flexibility using agile and lightweight method. So this is the outline of our steps for Agile model-driven re-engineering approach. So we have 5 main steps that we have followed. The first step is from, we try to abstract the source programs into semantic models using ANTLR and CSTL. And then we try to refactor our approach using quality analysis, restructure, and re-architecture, and then we try to extract the semantic models into requirement specifications, and finally we generate executable code and test cases into a target platform. So here are the main steps. As we said, step 1, ANTLR parser engine and CSTL text to transformation to UML and OCL. And then we try to maintain semantic preservation refactoring to abstract specifications, while step 3, we try to link the system requirements to the abstracted system models, and 4 and 5, generating the executable code and the test cases. So we have 2 main research questions this paper is gonna address. Research question 1, can effective and reliable re-engineering process to support it using ANTLR and be supported using ANTLR and CSTL? The second research question, does approach significantly reduce manual workload of re-engineering tasks? And as we said, that our overall aim is to reduce the human effort and resources needed for the re-engineering process. So the main challenges of legacy code abstraction in general, we know that COBOL and VP legacy code used for business critical finance and banking system. They have antiquated constructs such as go-to and large and complex. Visual Basic has also implicit typing, while COBOL, they have byte format typing. And we know that VP code can depend on Excel sheet. For example, our case study, as we said, it has been used since 1990s. with 2,000 line of code and mainly used in a spreadsheet, and we have some pictures for that. So for program abstraction, first we have the source languages using AML and parser, while the target language is UML and OCL. For example, for a COBOL statement, add PQR to VX rounded, it has been abstracted, example, using VX equal VX plus P plus Q plus R applies to round to N, where N is the number of fraction digits of a VX type. Here, for example, we have a table for VP6, VP8 constructs and how it has been abstracted to UML and OCL. For example, module, we have abstracted to package, while record to classes, for each, and for example, for, and so on. And this is a continuation of the same table with different constructs and its abstraction. Also, here we have abstraction, but for COBOL to UML OCL. For example, we have program suites to package, F evaluates to F, and so on. And also, this is a continuation for the same for COBOL constructs into abstraction in UML OCL. Here, for example, we have for quality analysis and restructuring, we have many technical depths that we have used and how we refactor to solve this issue or to reduce and minimize the number of flows. For example, in ENO, the excessive number of operations, we try to split classes, while, for example, in high synchromatics complexity, we split operations. Also, here we have other flows. For example, duplicate code expressions, we refactor using factor duplicates just to make sure that the code is located in one place instead of having them in many places, and so on. For re-architecting, we try to replace the one big code or one monolithic code by restructuring the code into new modules to package them or group them to enhance the cohesion and coupling of the approach. Also, there are some interfaces that have been introduced to remove direct dependencies, and also the platform-specific code has been factored out, and also we have applied or try to maintain the three main clean architecture properties, which are ADP, no cycle of dependencies, ISP, interface segregations, and DR, which is dependency rules. So we have established in this approach. Here is an example of how we re-architect the original code. As you can see, these black circles and arrows are the original functions. It has been, or it used to be, monolithic code, and these red squares is the new modules that we re-architect to just make them group these functions and into new modules to enhance their cohesion. So we have C1, C0, C1, C2, and C3. For evaluation, as we said, we have two different case studies, one in VP6, VP and VP6 to Python, and also COBOL. So for the first research questions, can effective and reliable engineering process be supported using Antler and CSTL? We have applied the Agile model-driven reverse engineering process to, as I said, translation of VP6 to Python and COBOL to Java and C#. There is also computational accuracy measures we have applied to make sure that percentage of testers which return same results for source and targeted, we are gonna show shortly. And also we have make sure that the clean architecture properties are maintained using index cohesion measure CRA. For example, for the VP6 VPA re-engineering case studies, for the accuracy, for example, we have 100 VP examples translated to Python, including bond application, which has 2,000 line of code. We have three different categories: the languages, the functions, and the bond applications. Here we have the number of cases and the tested and the translation accuracy for these tests and cases. For example, for language, we have 60 cases and 123 test cases, which are mainly 2 test cases for each case. We can see that 81% of the test cases have passed the test, while 70% of the cases also they give the same result for the source and target. For the function, 74 test cases we have where 82 of these test cases have passed. And for the bond applications, we have 51 test cases where 90% of these tests have passed, with a total number of 84 of these test cases have passed, indicating high accuracy. As I said, this is the Excel sheet for the original VP case. As you can see, the parameter, the number of steps, and how we abstracted that into the, and also here we have the example for the code, the original code, and how it has been translated into Python. This is the outcome. Okay, so that's for the accuracy. For the quality improvements of the case studies, we have original CRA is 0.18, and for the re-architected, you can see it's 0.97. It has been improved. So we have significant flaws in original code and including overlong routines, unused variables, and cloned code. So as you can see, here are the 3 properties of the clean architecture. So with so we have here actually 10 cases, and all the cases for dependency rules. For dependency rules, only 80% they have passed, while for the interface segregation, 100% they have passed, and for the ADP, 100% they have passed also the test. As you can see here, the significant reductions of flaws for the original code, okay, with different technical depths. For example, for duplicate code, we have 15, while the restructured, we have only 8. Excessive fan out, we have 2, and it has been reduced to 0. And magic numbers, we have 103 in the original code, while for restructured, we have 0. As you said, the significant reduction in the number of flaws. For example, here for our second case study, which is COBOL, we have 100 examples of COBOL code translated to Java, 100 translated to Java, while 50 has been translated to C#. As you said, as you can see, that we have compared the accuracy of the first version in Java to the C#. Also, we have 3 different categories for the COBOL: the statements, language, and functions. Also, we have cases and tests as well. For example, in Java, 93 of 138 cases have passed the test, while in C#, 94 have passed the test. For the languages, for example, 78 and 91 respectively have passed the test. And 82 of the functions in Java have passed the test, while in C#, 96. You can see there is quite, an improved in the accuracy of C# compared to Java. That's because actually Java has been implemented first and then C#. So this is second iteration, which has improved, in the accuracy for C#. For our second research question, does approach significantly reduce manual workload of re-engineering tasks? The answer is yes, by automating most of the steps of the reverse engineering process. For example, for abstraction, analysis, and code synthesis and test generation, we have full automation, while for restructured and re-architecture, we have partial automation. With the support of these tools. For example, for abstraction, we have bit via Antler and CSTL, while for structure, we have partial support for manual selection of restriction actions. And for code synthesis, we have it using Agile UML tool, which has been implemented by Lano, and the test generation using model-based testing tool. For related and future work, here we have the list of the related work and the approaches they have used compared to against to our approach. For example, here, Remix, they have modernization migration. They have, for example, they have used Agile as we did, but most of these related work, they have actually focused on the translation from one program to another, not semantic preservation, while our approach, we focus on, in addition to the translation, only and also the semantic preservation of the code. So our approach can be distinguished using the construction of semantic intermediate representation in a standard software language instead of repository of syntactic data and meta model, and also re-architecting the facilities linked to clean architecture qualities for quality improvement, and finally user adaptable and lightweight tools, so with the need only for grammar expertise, not MDE expertise. For our future work, we try to focus more on machine languages for learning abstraction mapping via simple machine learning and large language models. Thank you so much for listening, and any question?